Thank you, Professor Ifi. This is Krishna Acharya from UT Arlington. I'm a PhD student under the supervision of Professor Liu. Thank you for joining this session. I know we are already behind the schedule, so I'll try to manage the time not to make long. Okay, my topic is Liutex-based modification of Vreman's model for large eddy simulation. In this presentation, I basically going to discuss about the basic theoretical structure and the general concept rather than numerical computational line graphs. So it's the general theoretical framework. Let us start from the general concept or knowledge of the basic terms like DNS, eddy, etc. As you all are familiar with the DNS, direct numerical simulation is the fundamental computational method in computational fluid dynamics for solving fluid flow. An eddy is simply defined as a rotation of fluid, a circular water movement counter to a main current. Similarly, viscosity is a measure of fluid's resistance to flow or the strength of the vortex. It describes the internal friction within a moving fluid that arises from intermolecular forces in liquids and molecular collisions in gases. A vortex is a region in fluid in which the flow revolves around an axis lines. Of course, this is a vortex. It is the main center point of the discussion of this conference. So in this presentation, I'm going to discuss a little bit about these three models: Chemronsky model, Vreman model, and modified Vreman model. The Chemronsky model, introduced in the year 1963, is one of the first and most widely commonly used large eddy simulation subgrid stress models. The model is based on the concept of eddy viscosity. The model is used to simulate turbulent flows. It is simple and computationally efficient. It is one of the subgrid scale models that is used in large eddy simulation transitional flow. The turbulent viscosity hypothesis assumes a linear relation between eddy viscosity and the magnitude of the large-scale deformation tensor. It relies on the shear rate magnitude. It often fails near solid walls because it mistakes high laminar shear for turbulence, leading to over-dissipation. Chemronskys offer robustness but tend to over-dissipate, especially in rotational regions. This is one of the limitations of the model Chemronsky. Similarly, the model Vreman, introduced in the year 2004, is an eddy viscosity subgrid scale model of turbulent shear flow for large eddy simulation. It is an algebraic eddy viscosity SGS model. It provides a way to represent the effect of unresolved small-scale eddies on the larger resolved scales of motion. It is rotationally invariant. Vreman model can achieve accurate results for both homogeneous and transitional turbulence, even in near-wall regions, by ensuring the subgrid scale dissipation vanishes in laminar flow. The Vreman model uses the Bosnick hypothesis to relate the soft grid scale stress tensor to the resolved strain rate. It offers a computationally less expensive alternative. The Vreman model proposes a specific algebraic form for the eddy viscosity that is a function of the local velocity gradient and grid size. The model is simpler to implement because it does not require the explicit application of filtering operations or averaging procedures. The model ensures eddy viscosity vanishes in laminar shear flow. The model is based on the full velocity gradient tensor, which mathematically includes shear deformation, leading to inaccuracies in complex vortex-dominated flow. Vreman's formulation remains fundamentally dissipative and does not fully distinguish between real turbulence and rigid body rotation. This is one of the limitations of Vreman's model. Now, modified Vreman or Liutex-based Vreman model. Liutex is a mathematical definition of local fluid rotation or vortex, which is a vector representing rigid body rotation. It is an advanced soft grid scale stress model which modifies the classic Vreman model by integrating Liutex to define eddy viscosity. This modification eliminates the contamination of shear found in traditional vorticity-based models, which results in higher accuracy for transitional flows, rotating flows, and wall-bounded turbulence. It addresses Vreman's limitations by explicitly incorporating a mathematically rigorous measure of fluid rotation, which is known as a Liutex. Theoretical framework of eddy viscosity modeling. Vreman's eddy viscosity model, SGS model, was designed around a structural requirement that the SGS eddy viscosity should be small or zero in flow configurations. LES with an eddy viscosity closure solves the following filtered Navier-Stokes equations, and these equations are taken from the Vreman 2004 paper, which is partial uj bar equals 0, delta t ui bar plus delta j ui bar uj bar is equal to negative of delta j parenthesis p bar plus tau kk over 3 plus v delta square j ui plus delta j 2 nu e sij. The unknown turbulent stress tensor is defined or given by the formula tau ij is equal to ui uj bar minus ui bar uj bar. And this tau ij is replaced by the model negative 2 nu e sij plus tau kk delta ij over 3, and where sij is defined by half of sum delta uj bar plus delta j ui bar. The original Vreman eddy viscosity model is defined by the formula nu e is equal to constant c square root b beta divided by alpha ij, and where alpha ij, beta ij are defined as this formula shown in the screen. I want to reduce the time. The theoretical framework of the Liutex-based modification Vremans model is built upon the intersection of large eddy simulation, closure theory, and vortex identification theory. When solving Navier-Stokes equations, this process separates the flow into resolved scales known as large eddies and soft-grid scales known as small eddies, and introduces an unclosed term, the subgrid scale stress tensor tau ij, which is equal to ui uj bar minus ui bar uj bar. The Liutex framework proposes a clear decomposition nabla u is equal to r plus s and r, where nabla u denotes the velocity gradient tensor, r denotes pure rigid body rotation known as Liutex, S denotes symmetric strain or shear, and S and R denotes antisymmetric shear. This modification eliminates the contamination of shear found in traditional vorticity-based models, which results in higher accuracy for transitional flows, rotating flows, and wall-bounded turbulence. It addresses Vreman's limitations by explicitly incorporating a mathematically rigorous measure of fluid rotation, which is known as Liutex. SGS dissipation should only be active when R is positive. The modification integrates the Liutex magnitude into the eddy viscosity scaling. The fundamental difference between the Liutex-based modification and the original Vreman model is the definition of the local rotation. Liutex extracts only the rigid body rotation. The magnitude of the Liutex factor, denoted by R, represents the angular speed of the rigid rotation. Liutex modified Vreman's SGS viscosity is defined as nu TL is equal to C delta square function of beta absolute R, where R is Liutex magnitude. Absolute R is the strong, when absolute R is large, it is strong vortex core, and when absolute R is 0, it will be pure shear or strain. The function f is designed so that SGS viscosity decreases as Liutex increases, so that vortice is preserved, and SGS viscosity increases with strain intensity dissipation added where needed. A common functional choice is nu TL is equal to nu T for man 1 minus G absolute R, where G absolute R is equal to absolute R over R plus S is the vortex suppression factor, and S is the stress magnitude. This makes the eddy viscosity high when strain dominates needed for turbulence cascade, and low when pure rotation dominates protects vortex course. Liutex is non-zero in rigid body rotation, but strain is low. The modification ensures that inside vortex core, nu TL tends to 0, approaches to 0 inside vortex cores. This ensures LES retains physically meaningful coherent vortices. Let's talk about application. Vreman 2004 eddy viscosity model successfully applied to transitional and turbulent mixing layers at high Reynolds numbers and a turbulent channel flow at RE tau is equal to 360. It can handle the complications caused by high Reynolds numbers, transition, and walls. The model is relatively easy to implement and quantifies that it leads to satisfactory results even for low-order schemes and is therefore suited for engineering applications. Similarly, Liutex-based Vreman is more advanced. It is not just a theoretical improvement, it is a high-fidelity tool to design for engineering problems where flow transition and vortex dynamics are critical. It removes shear contamination from the eddy viscosity calculation. This model means the modified model allows engineers to simulate complex flows with lower grid resolutions while maintaining higher physical accuracy than standard Samnonsky or dynamic models. It can predict accurate transition points on airfoils, turbine blades, and drone propellers without requiring expensive DNS in aerospace engineering. It can also be implemented in CFD into a solver like OpenFOAM or ANSYS. Remain viscosity using the Liutex magnitude. The model systematically reduces dissipation in vortex cores while maintaining or enhancing dissipation in strain-dominated regions. Liutex Vreman provides a vital bridge between theoretical fluid dynamics and real engineering design. Let us conclude for the three models: Samnonsky model, Vreman model, and Liutex Vreman model. There are 4 columns. The first column describes its aspect or feature. The second one, Samnonsky model, third one, Vreman model, and the fourth, Liutex Vreman model. The type. Samnonsky, classical eddy viscosity. Vreman, invariant-based algebraic eddy viscosity. Liutex Vreman, rotation-aware, Liutex modulated Vreman model. Core idea, Samnonsky, SGS viscosity is proportional to strain magnitude. Vreman model, SGS viscosity based on velocity gradient invariance that vanish in zero dissipation states. Liutex Vreman reduce SGS viscosity in vortex cores via Liutex, preserve rotation while enhancing strain-based dissipation. Ability to distinguish strain versus rotation, Vreman, poor, vorticity and strain both increase viscosity. Vreman, moderate, some zero dissipation conditions remove false viscosity. Liutex, strong, explicitly separates rigid body rotation via Liutex. Behavior in pure shear. Samnonsky, over dissipative. Vreman, correctly low dissipation. Liutex Vreman, same as Vreman, that is low dissipation. Behavior in vortex cores. Samnonsky, over dissipative, it destroys vortices. Vreman, better than Samnonsky, but is still dissipative. And Liutex, very low dissipation that leads to preserves coherent vortices. Near wall behavior. Samnonsky requires wall damping or low constant CS. Vreman naturally reduces viscosity near the wall. Modified, even stronger natural reduction due to Liutex is zero near walls. Transition prediction. Samnonsky, poor, suppresses transitional structures. Vreman, it is improved. Modified Vreman or Liutex, best of the three, strong vortex preservation. Turbulent shear flows. Excessive damping, tailored for shear, performs well. Liutex, similar or improved compared to Vreman. Computational cost. Lowest, low, similar to Samnonsky. In modified, slightly higher than Vreman, but still lower computational cost comparable to fine grid simulations and coarser meshes by not wasting dissipation on laminar shear. Numerical stability, Samronsky very robust, Vreman robust, Liutex Vreman good, but the Liutex calculation requires careful implementation. Backscatter, none by default, but vortex preservation indirectly mimics mild backscatter. Rotational invariance, all three models, yes. Filter requirements, Samronsky single grid filter, Vreman non-beyond grid, and modified Vreman non-beyond grid. Best application areas, Samronsky coarse alias simple engineering flows, Vreman shear flows, wall-bounded turbulence, and modified vortex-dominated flows, transitional turbine flows, jets, rotorcraft, OX, etc. The weakness, Samronsky over dissipation, everywhere poor vortex prediction, Vreman still dissipates in vortices, less rotation aware, and modified Vreman slightly costlier, requires careful Liutex implementation. Let us summarize the three models in a single line. Samronsky, the model is considered as simple, less expensive compared to others, robust, but over dissipates, especially near walls and inside vortices. Vreman model, it is improved than Samronsky shear sensitivity and near wall behavior. It avoids many false dissipation states. And Liutex Vreman, the most physically refined, explicitly preserves rotational structures while retaining Vreman's good strain behavior. As my contact info, thank you for listening. Thank you for your attention, and also thank you for joining this session.